So welcome to the 75th anniversary of NASA Ames Research and the Directors Colloquia Summer Series. Our species is a specialist evolved to use our environment in novel ways in order to expand our capability to survive new environments. Our species also owes its survival to the ability to predict dangers and to counter them. Our home planet, and currently our only home planet, Earth, is changing in a way that poses a potential danger to our long-term survival. Whether it's due to natural, man-made, or a combination of causes, we need to find solutions. Today's presentation is entitled Roadmaps for Transitioning All 50 U.S. States to Wind, Water, and Solar Power. Will be presented by Dr. Mark Jacobson. Dr. Jacobson is the director of the Atmosphere and Energy Program and professor of Civil and Environmental Engineering at Stanford University. He is also a senior fellow of the Woods Institute for Environment and of the Precourt Institute for Energy. Dr. Jacobson received a BS in Civil Engineering, an AB in Economics, and an MS in Environmental Engineering from Stanford. He also received an MS and a PhD in Atmospheric Sciences from UCLA. Dr. Jacobson is an author of 2 textbooks and has over 140 peer-reviewed articles. For his work, he has received numerous awards, including the 2005 American Meteorological Society Henry G. Houghton Award and the 2013 American Geophysical Union Ascent Award and the Green Global Policy Design Award. Please join me in welcoming Dr. Mark Jacobson.
Thank you very much, Jacob, for that very kind introduction. And so I want to talk today about energy plans that we've been developing and hope to implement on changing the energy infrastructure of the United States and ultimately the whole world. And I'll start with what's the problem, some motivation. So I'll look at the problem first and then get into the solutions. And I probably don't have to convince you that there are problems, but some audiences, you sometimes have to convince them. But we look at it from an air pollution, global warming, and energy security point of view. And in the United States, about 63,000 people die every year prematurely from air pollution, and hundreds of thousands more become ill due to air pollution. And this costs the U.S. about 3.2% of the GDP, looking at based on statistical cost of life and illness. And worldwide, there are about 3 to 7 million people die prematurely each year. And almost all this air pollution is due to fossil fuel emissions and biofuel emissions. And global warming, of course, is a growing problem and already causing significant damage. And in terms of monetary costs, it's one estimate, and there are a lot of different estimates out there, is by 2050, about $730 billion per year from just US emissions alone. And these are worldwide costs of $730 billion. Other problems are that fossil fuels are finite resources, and their costs are going up because there's a fuel cost that keeps growing. In comparison, renewable energy such as wind and solar power in particular, or geothermal, hydroelectric, the fuel cost is 0, so you can expect you might be able to stabilize energy prices by going to those fuels. Jobs is another issue, and as we'll see, with the fossil fuel industry, you're actually causing job stagnation because there's actually fewer jobs associated with that than in burgeoning wind, water, solar industries. So I'll give you numbers on that. So these are all drastic problems because you can imagine if prices go up over time of fuels, then that would eventually, if the prices get beyond a certain level, then you can get not only economic and social instability, but also political instability and possibly civil war. So these are all drastic problems that require drastic solutions. And the solutions that I'm going to talk about are wind, water, solar solutions. These will all eliminate air pollution death, eliminate almost all global warming, and provide job and energy security and price security. So let's just look a little bit more at the problems. In the United States, we look around and we see, well, it doesn't look that dirty. How do people die from air pollution? Well, you can actually just look at take measurements of the pollution levels at all the monitoring stations in the US and look at epidemiological data that has been gathered for the last 40 years or so, and apply dose-response relationships and look at the populations that are exposed to the concentrations. And this is where you get about 60,000 deaths per year in the US. But in places like China, there are about 1 million deaths alone prematurely each year. And Beijing, this is a photo of Beijing, China, and you can kind of really see and visualize the pollution. It's like smoking 2 to 3 packs of cigarettes per day. And if you think that's unusual, in Los Angeles in the 1970s, it was equivalent to smoking 2 packs of cigarettes a day. And these are the lungs of a teenage non-smoker who died in a car crash living in Los Angeles in the 1970s. So, generally, even today in the United States, a person who lives in a big city loses about 6 to 8 months of their life prematurely on average due to mostly particulate matter, but also ozone and some carcinogens. So pollution is still a major problem. In terms of climate, this graph shows the temperature change in recent years compared to 1900, and compared to the 1900 to 1920 average. And the data aren't great, but what it does indicate about a 0.9 degree warming, that's 0.9 degrees Celsius warming of the climate. And most of the warming is in the northern hemisphere, and particularly over the Arctic. So the Arctic sea ice is disappearing rapidly as a result of this higher temperatures. And if it melts entirely, you can expect positive feedback as you uncover the dark ocean below. Now, one of the problems with, it's not only CO2 and other greenhouse gases that are causing melting of the Arctic, but it's also things like black carbon, which is a main component of soot, which is emitted from diesel exhaust, jet aircraft, kerosene burning, and biofuel and biomass burning. And the darkening of snow and sea ice increases its melt rate. In fact, black carbon, not only due to its darkening of snow, but its impacts because in the air, black carbon is 1 million times more powerful per unit mass at warming the air than carbon dioxide, but has a much shorter lifetime. But it not only melts the Arctic, it warms the air directly, but it also evaporates clouds. So you can get in regions of China, for example, you don't have real clouds anymore just because you have so much black carbon that evaporates the clouds, causing them to become more hazy, and more solar radiation then reaches the surface, warming the surface faster in a positive feedback loop. Well, this black carbon, one of the main emitters, or one of the growing emitters is, for example, natural gas burning, flaring. And so you have all these flares that are putting out black carbon, but you also have a lot of diesel exhaust. So we'll get into kind of the energy solutions that have been proposed that aren't so great, so natural gas would be one of them. In terms of climate, global temperatures are rising fast, as I mentioned, and we saw the anomaly is about 0.9 degrees since the early 1900s. But this just shows an average trend indicating the same thing, but kind of showing how in more recent years, in the last 30, 40 years, there's been an acceleration of warming. It's not that we haven't had, in the past, people who deny global warming have said, well, temperatures have been warmer in the past, and that's true. 100 million years ago, the Earth was ice-free. But of course, nobody lived back then. So it didn't cause all the melting of the ice, which today, if you melted all the ice worldwide, you'd have 70 meters more of higher sea level, and that would cover 7% of the world's land, and most people live along the coast. So the problem is we have warming in the presence of 7 billion people on Earth, and this is a great problem because it would cause not only large population shifts due to covering of the coastlines, but also lots of heat stress and heat stroke, changes in agriculture, acidification of the oceans, increased air pollution, increased severe storminess, etc. So all these problems associated with global warming have costs associated with it. Now, if we look at net observed global warming which, as I mentioned, is on the order of, well, it's on the order of 0.9 degrees or 0.8, depending on which data you look at. That's this right bar is a net observed warming. That's really a combination of greenhouse gas warming on the left, which is over 2 degrees Celsius, and fossil fuel and biofuel soot warming, which is on the order of 0.5 degree Celsius, and a little bit of urban heat island effect, but minus cooling due to air pollution particles that are reflective, such as sulfates and nitrates and some certain organic matter and associated water and ammonia. And these cooling particles offset about half of the global warming, so that's why you have a smaller net observed global warming than the greenhouse gases cause. But you can immediately see some major problems here. If we just clean up air pollution particles, we'll clean up the fossil fuel and biofuel soot particles plus the cooling particles, and all of a sudden we would double the global warming that's occurring. So the warming that's in this system, half the warming is being masked by pollution. That's causing 3 to 7 million deaths per year. But we want to clean up that pollution to prevent these deaths. But doing so would uncover all this warming in the system and cause rapid acceleration of the temperatures of the climate. Now, the other possible solution, so one possible solution is just to focus on the soot particles, because the greenhouse gases last so long that even if we eliminated their emissions today, we wouldn't, for example, slow the melting of the Arctic ice, which will disappear within 10 to 30 years. But if we reduce the fossil fuel soot emissions, then, which have a short lifetime, we can actually reduce both pollution particles that cause health problems, and we can reduce warming. So that's one strategy. However, it doesn't address the long-term health of the planet or most of the pollution particles that cause health problems. So the other solution is just to eliminate all the pollution, all the greenhouse gases, all the fossil fuel and biofuel soot, and all the cooling particles simultaneously. And that's the solution we're going to focus on today. So how do we do that? Well, a few years ago we did this study looking at, well, what are potentially the best solutions to global warming, air pollution, and energy security, just in terms of cleaning up the problem, not in terms of the costs. And what came out of this was a ranking in terms of, well, we looked at a lot of different impacts on the pollution, on global climate, on land use, on water supply, on catastrophic risk, on reliability, and some other factors. And the technologies that came out on top in terms of electric power were wind power, solar, photovoltaics, and concentrated solar power, geothermal power, hydroelectric power to the extent it exists, and some tidal and wave power. In terms of transportation, it was battery electric vehicles being where the electricity was coming from these, what we call wind, water, and solar, or WWS, electricity options. And hydrogen fuel cell vehicles where the hydrogen also came from electrolysis where the electricity came from the wind, water, solar options. And for aircraft, possibly cryogenic hydrogen, which was used in the space shuttle to propel it into space, although that would probably be the last things that has changed. For heating and cooling, we'd use these clean electricity options to run air source, ground source, and water source heat pumps, not only for air heating and air conditioning, because they can be run in reverse for air conditioning, but also for water heating. And you can have solar water preheaters, some electric resistance heating, but that's less efficient than heat pumps. For industry, where you need high temperature processes, you can have electric resistance or hydrogen combustion, where the hydrogen is produced from clean electricity. So these are all the options that we're going to be looking at in the numbers I'll present later. But you might ask, well, why don't we include things like biofuels or nuclear power or natural gas? And so what was not recommended in this analysis was nuclear power or coal with carbon capture and sequestration, natural gas or biomass for electricity, or for vehicles, liquid biofuels such as corn or cellulosic or sugarcane ethanol, or soy or algae biodiesel or compressed natural gas. And so you might ask why? Well, why not natural gas? In terms of, well, first of all, we think of everything in terms of opportunity cost. You know, we're not going to be comparing natural gas and coal. We could do that, but it's really, we're comparing natural gas versus wind or solar. So if we compare it to wind, for example, natural gas puts out 50 to 70 times more carbon dioxide equivalent emissions and air pollutants per kilowatt hour of electricity generated than wind does. And not only that, it's putting out a lot of the black carbon from flaring and methane from leakage that has, the methane has a relatively shorter lifetime than carbon dioxide on the order of 8 to 12 years. But it's one of those two, black carbon and methane are, if you want to control the Arctic sea ice loss, those are really the only two ways you can control it, eliminating black carbon, eliminating methane. But natural gas actually contributes to both. Due to, in the case of natural gas, there's a leakage rate. If it's conventional gas, it's on the order of 1 to 2% of all gas is leaked. But if it's non-conventional, such as from hydrofracking, you get leakage rates that are anywhere up to, there's some studies that go up to 9%, but more likely 4 to 6% leakage. Natural gas mining, transport, and use causes about 5,000 premature deaths per year in the US. And that's from the combustion products of, like for example, when you're mining, you use a lot of fossil fuels to get the gas out. And so there's a health problem associated with, there's emissions, and then there's water supply and land use, as you can see from the photograph there. I mean, there are tens of thousands of wells alone for hydrofrac gas in Pennsylvania. And about 5% of all fracked wells, the cement casings leak immediately. And about 50% leak over the lifetimes of the well. So you can imagine having tens of thousands of wells in each state, like in Pennsylvania, as I mentioned, you have like 70,000. And half of those wells are going to leak over their lifetime, just the cement casings alone. In any case, this is a problem, and it's not a sustainable future. Why not what's called clean coal, or coal with carbon capture? Well, that's where you take the CO2 emissions from the exhaust stream of the coal-fired power plant, you pump it underground, and that would reduce 85 to 90% of the CO2 emissions from the stack. However, it does not reduce any of the emissions of CO2 from the upstream mining and transport of the coal, which is about a third of the emissions. In fact, it increases that 25% because it takes 25% more energy, thus 25% more coal to run the carbon capture equipment. And it also does not, the carbon capture equipment does not reduce any of the other pollutants from coal. In fact, it has to increase it 25%. So you end up getting about 150 times more air pollution per kilowatt hour than wind. And so it should really be called dirty coal rather than clean coal. Now, why not what's called nuclear power? So nuclear, well, it seems clean because you don't have direct emissions associated with its use. However, you need to mine and refine uranium continuously over the lifetime of the nuclear power plant. And that's an energy-intensive process. And then it also takes so long to put up a new nuclear power plant, between 10 and 19 years in the US. And that's broken down into 6 to 10 years for permitting and another 4 to 9 years for construction. This is all compared to about 2 to 5 years total for a wind or solar farm. So while you're waiting around for your nuclear plant to be put up, you're running the regular electric power grid, which is mostly coal and gas. And so that's an opportunity cost emissions. When you combine that with the energy required and emissions associated with the mining and refining of uranium plus the construction of the plant, which is not a great part of it, you get about 9 to 25 times more CO2 equivalent emissions per kilowatt hour generated than wind power. Well, there's also, of course, the risk of meltdown. 1.5% of all nuclear reactors ever built to date have melted down to some degree. And 5 countries of the world have secretly developed nuclear weapons under the guise of civilian nuclear energy programs. So if you wanted to power the entire world with nuclear, you would need about 16,000, 17,000 large nuclear power plants, and we have about 440 today. So even if we doubled the number today to 800 or so, that would be about 5% of the world's energy. And more countries of the world would possibly try to develop weapons secretly. So there's a risk of proliferation, which you have no such risk with wind, water, solar technologies. Of course, there's the unresolved waste issues. Well, what about biofuels? Well, cellulosic ethanol and corn ethanol are examples of biofuels that have been proposed to be used on large scales. Now, for transportation. But just to give you an idea how much land area it takes alone, let alone all the other issues, if you wanted to power all the US vehicles with cellulosic ethanol, which is a second generation ethanol, which by the way does not actually exist at any commercial scale, although it's been proposed since 1980, this is the land area it would take. which is on the order of 20% of the entire US, including Alaska. And now there's a low estimate and a high estimate here. The low estimate's from the ethanol industry and the high estimate's from some science studies. But this is an average of the two. Anyway, so it's a large land area, but if you burn the ethanol, you still get the same pollution as you do with gasoline. In fact, in terms of ozone, it's slightly worse in the US. It doesn't matter where the ethanol comes from. So you actually cause about 4% higher death rates in the US from ozone by using ethanol of any type than gasoline. So it's not helping in terms of air pollution. And the climate benefit is kind of marginal because depending on whether or not you count for land use change. Now, in terms of corn ethanol, there's a little more uncertainty, and it's about 14% of the US to power the entire US vehicle fleet. So it's still a large area, and you require about 13% of the US water supply to do the same thing, and you have the air pollution issues, and probably the climate benefit is virtually zero. It's maybe 2 to 5%, depending on whose study you look at. Now, nuclear power, it would take about the size of Rhode Island to power the same vehicle fleet. So that's not one of its problems, unless we want to sacrifice Rhode Island for that. But if we look at other options, so wind to power the whole US vehicle fleet would take, well, there's two types of areas. There's the footprint, which is the land on the ground that's taken up by the turbine tower and the cement casing around it. So that's referred to as the footprint. And then there's the spacing, which is space you need between turbines to prevent interference of one turbine with the next. So the black on here is the spacing, and the red dot in the center is the footprint. So it would require, the spacing area is about 1/30th that of corn ethanol to power the same vehicle fleet. And the footprint area is about 1/millionth. It's only 1 to 3 square kilometers of land on the ground to power the entire US vehicle fleet with wind. And that would be with about 73,000 to 144,000 5-megawatt wind turbines operating in wind speeds of 7 to 8.5 meters per second, which those wind speeds you can find over about 13% of the US. So you need only 1/2 of 1% of the US land area for spacing of wind turbines to power the vehicle fleet, and you have about 13%. So you have 26 times more area than you need to do that. Now, a lot of this could also go offshore, where you have even more wind and more space. Now, in terms of other solar PV to power battery electric vehicles would take 1/3 the spacing area of wind, but if it's not on rooftops, and you can't put it all on rooftops, as I'll show later, then it's more footprint but less spacing. And geothermal would take even less spacing area than wind, but still more footprint. But we're going to be looking at wind and geothermal and solar as possible options. So they all take a relatively little space to do this, to run the vehicle fleet. But we're going to be looking now at powering the entire US for all purposes. So let's give some overall numbers worldwide and in the US. So in 2010, the end-use power demand worldwide in terawatts, or trillion watts, this is end uses, including electricity, transportation, heating and cooling, and industry, and what people actually use to run things, is about 13 terawatts. If you go to 2050, the projection is about 21.6 terawatts. But if you convert everything to wind, water, solar, and electricity and electrolytic hydrogen, you go down about 30% of your power demand, and only about 5 percentage points of this 30% is due to end-use energy efficiency improvements. The 25% is due to the efficiency of electricity over combustion. And you can tell about this electricity efficiency by when you look at converting transportation. So the plug-to-wheel efficiency of an electric car is about 80 to 86%. In other words, 80 to 86% of the electricity going into a car goes to move the car, the rest is waste heat. And in an internal combustion engine, the tank-to-wheel efficiency is about 17 to 20%, so about 80 to 83% of the energy in the gasoline is wasted as heat, and 17 to 20% goes to move the car. So you use 1/4 to 1/5 the energy driving an electric car the same distance as driving a gasoline car. So it costs about 1/4 to 1/5 to drive the electric car in terms of the fuel. So in other words, it's about 80 cents a gallon equivalent for driving an electric car compared to $4 a gallon for a gasoline car. So if you drove an electric car for 15 years, 15,000 miles per year, you would save about $20,000 in fuel costs. And that's because of the efficiency. So transportation is one sector where you get most of the efficiency. So that's why, just by converting to electricity, you reduce your energy use. And in the US, because there's more transportation than in the world as a whole, you go down 37.6% in your energy demand. And about 5 percentage points of that is, again, end use efficiency. In California, because there's more transportation in California than even in the US, it's about 44% reduction of power demand just by going to electricity. So here's one way to power the world with these wind, water, solar technologies. This is for 2030. This would be 50% wind, 40% solar, and the solar would be divided into rooftop systems, 6%, PV power plants about 14%, and CSP power plants about 20%, although probably revised those distributions now. And about 10% for everything else, including 4% hydro, 4% geothermal, 1% wave, and tidal. And so the wind would be about 3.8 million 5-megawatt wind turbines. Sounds like a lot, but this is to power half the world for all purposes, that's everything, in 2030. And the US in World War II produced about 330,000 aircraft each year, and the world produced, 330,000 aircraft during the whole war, and the world produced about 800,000. And every year, the world produces about 70 million automobiles. So just producing 4 million wind turbines to power half the world should not be a great feat. But there's a lot of politics going into play here. So let's look at it a little more closely. What about the US? To power the entire United States for all purposes, and this is based on, we actually did plans for every single state individually, and this is the sum result, and I'll show you a map of the results. This is one way to do it, and you can do it in other ways too. This would be 31% onshore wind, 19% offshore wind, and then residential rooftop systems is almost 5%, commercial government PV rooftop systems about 4%, so on the order of 8.5% rooftop solar. Now we actually went through every state and calculated the rooftop areas in every state, and including the parking structure potential areas, and then projected to 2050 to get these numbers. So this is saturating all the roofs. So you can power for the whole purpose, all purposes, US in 2050 with probably no more than 8.5 or 9%. You might be able to squeeze up to 10% rooftop solar. So we want to do as much as possible. If we can do more, that's great, but you're not going to be able to, distributed energy can only go so far. You will need power plants as well. So that's why we have power plant PVs like in deserts and concentrated solar power in deserts. So about 29.6% of the plan here across states is solar PV plants. Another 8% is CSP or concentrated solar plants. And then geothermal is about 1.3%. This is accounting for potential growth of geothermal. And hydro is about 2.5%. Now this is not just electricity, again, this is all power. Right now, hydro powers about 6.5% of all US electricity. But electricity is only about 1/5 of total energy. So it's only producing about 1%, 1.5% of total energy. And so we'd be doubling basically the hydro without actually increasing any plants. This plan has virtually no increase in the number of hydroelectric plants, except for in Alaska, where there's those 4 plants listed there would all be in Alaska. Because we're just planning to have the existing hydro, but increase the efficiency, possibly taking some non-power dams and making them power dams, but not actually putting new dams in. Then there's a small amount of tidal and wave power. So how much land area does this take? So this is the land area required. The green in the center is for onshore wind, and that's mostly spacing area, which is 31% of the total energy or power. The footprint would be about 4.5 square kilometers on the ground. And the spacing area is about 1.7% of the US. Offshore wind is about 19% of the total. PV plus CSP power plants is 37% in that orange dot, but the land area is about 0.4% of the US. Rooftop PV, which would not require new land, is about 9% of the total power supply and about 0.09% of the land area. And then there's a small amount of hydro and tidal and wave. Just one more of these. Here's for California. California would be dominated more by solar in this case, but still 35% total wind with 25% onshore wind and 10% offshore. Rooftop solar and commercial government building solar, about 14% total of the total energy would be provided from there. PV power plants, 26%, 15% CSP power plants, 5% geothermal, 3.5% hydro, again, no new dams, and a small amount of tidal and wave. And this is what the land area is required and water area is required for a California energy plant. And so again, we did this for all 50 states. Well, in these plans, there'd be a lot of offshore wind. And we did a study, a computer modeling study looking at, well, what's the impact? Because you might ask, if you have a lot of wind turbines, do they interfere with each other? Maybe they take too much energy out of the wind and therefore can't provide all the energy. We did one study on that looking at if you saturate the US and the world with wind turbines, would you have enough energy still to power the world? Because each turbine takes energy from other turbines. But we found that in the world limit, you can cover the entire world with wind turbines, and the most energy or power you can extract is about 250 terawatts worldwide. That's over land and ocean. And we need about, on the order of 12 or so terawatts of power, and so to power the entire world. So there's plenty of wind worldwide to power the entire world, even if you have turbines right next to each other. Over land, there's about 80 terawatts of wind power available worldwide. So we won't run out of wind, but the key is to have wind farms separated from each other so wind farms themselves don't interfere with each other. You can have a lot of individual turbines in a wind farm, but you want to separate the wind farms far enough apart. But another question that arose is, well, what's the impact? If you have a lot of offshore winds off the East Coast, you get a lot of hurricanes. Won't the hurricanes destroy the wind turbines? And so we thought about this and then looked at the question, well, the turbines might be destroyed, but on the other hand, if you have enough turbines, maybe they'll feed back and extract enough energy from the hurricanes. So we did a case where we put wind turbines in a 3D weather model off the coast of New Orleans, and we looked at Hurricane Katrina and Isaac off New Orleans and Hurricane Sandy off New York and the East Coast. And here's one of the results. So in this case, we have the same hurricane, Hurricane Katrina. The left side is no wind turbines. On the right side, we had 170,000 7.5 megawatt turbines to the southeast of New Orleans. And we then produced the hurricane. We compared the hurricane with data when there were no turbines. And then what we found is the hurricanes were being diminished by when you have large arrays of offshore wind. So in this case, you can see in the right, that's kind of where that triangle is. That's where the turbines were located. And what happens is the turbines would extract energy from the hurricane, slow the wind speeds locally, reduce the wave heights, reduce convergence, because you need waves to produce friction that causes convergence of air to the center of the hurricane. So when you reduce the wind speeds locally, you reduce wave height, you reduce friction, so you reduce convergence to the center, so you increase the central pressure, and that caused a diminishment of the entire hurricane such that by the time the core got to New Orleans, the whole thing was pretty much diminished. And in fact, it reduced about 80% of the storm surge and in 50 to 60% of the wind speed at New Orleans. And we found this for all the hurricanes that we tested, we found this result. And also the wind speeds, in fact, when you had enough of them, never got up to the destruction wind speed of the turbines, which is 50 meters per second, because you feed back to the center of the hurricane so much that you just diminish all the winds locally. And I can go into detail on that, but I don't have time. But so the result was that if you have large arrays, you can have this impact, so you can have a benefit. Now you might say, well, that's going to be really expensive, but the thing is, you would put up the turbines to generate normal electric power year round, so they would pay for themselves. And so as a result, it would not cost extra to prevent the hurricane or reduce the damage of the hurricane. On the other hand, if you put up seawalls, they might cost $30 billion for one city. They don't generate electricity, so they don't pay for themselves. And they don't actually reduce wind speeds, they only reduce storm surge. And so you could take $30 billion and just buy wind turbines with them and get that money back over time So I think it's probably a better investment to go with offshore wind. Now, if you don't have enough turbines, you do run more risk of turbine destruction in the Gulf Coast, but not the East Coast, because in the East Coast, the wind speeds never get up to the destruction wind speed of the turbine in any case. Anyway, I'm going to move on from that. So what about the cost of energy if we do this conversion to wind, water, and solar? Well, on the left side here is the current cost of these different clean energy technologies. For wind, it's 4 to 10 cents a kilowatt hour. That's onshore wind. Offshore wind's 11 to 22 cents. Geothermal is about 10 to 15 cents. Hydro is about 4 to 6 cents a kilowatt hour. Concentrated solar is about 13.5 to 17. PV utility scale is 10 to 11 cents a kilowatt hour. Now, if we use the 2050 mix of wind, water, solar technologies that we want and apply them to these costs, then we get about 11.3 cents a kilowatt hour on average. And that compares to conventional fuels right now, 10 cents a kilowatt hour. But there's another 5 cents a kilowatt hour of externality or health and climate costs associated with that. So they're really 15 cents a kilowatt hour, although these utilities and the energy companies are getting a free ride for 5 cents a kilowatt hour. So right now, people can argue that wind, water, solar is more expensive if we converted everything. Except wind, onshore wind, geothermal, and hydro are cost competitive. In fact, onshore wind is the cheapest form of new electric power in the US right now, in the Great Plains. It's on the order of 2 cents a kilowatt hour subsidized and 3.5 cents unsubsidized, and that's less than natural gas. But if we go to 2030, because you stabilize the energy prices with wind, water, solar, because they have zero fuel costs, so their costs are all going down, whereas fossil fuels, if you just look at the trend for the last 10 years and you just project forward, you're going to get 17 cents a kilowatt hour for fossil fuels in 2030, plus another 6 cents for externality, so that's 23 cents a kilowatt hour. So in 2050, wind, water, solar will be on the average 6 cents a kilowatt hour versus 17 cents a kilowatt hour for the fossil fuels. And to just demonstrate we'll look at some of these cost benefits in a second, but I want to demonstrate how you stabilize prices in a second. But the additional benefit, the externality benefit of eliminating fossil fuels with wind, water, solar is in reducing air pollution health costs and climate costs. As I mentioned earlier, there are 63,000 people die prematurely each year, and that costs about $510 billion to the US, or 3.2% of its GDP. Global warming costs to the world from US emissions are about $730 billion by 2050. So these costs would be eliminated. But the costs change, just to demonstrate that you stabilize the actual direct cost of energy. If you look at the 11 states in the US with the highest fraction of electricity from wind, and the top two are Iowa and South Dakota with about 28% of all electricity from wind last year. Those states, the 11 states with the highest fraction of electric power from wind, have decreased in cost 0.4% in the last 5 years. All the other states went up 8%. Because wind has zero fuel costs, so it's all in capital costs. It has higher capital costs than fossil fuels, but lower fuel costs. So you know what the cost will be. It'll stay stable over time, whereas fossil fuel costs go up over time. In terms of jobs, we looked at each state to look at job creation versus lost, and used the NREL JEDI models to determine job creation, and looked at actual jobs that would be lost in fossil fuel industries. We found 5 million 40-year construction jobs would be created, and another 2.4 million operation jobs. So it's about 7.5 million jobs created versus 3.9 million jobs in the fossil and nuclear industries, which would be lost if we do this convergent. So there would be a net job gain. And then one more point I want to make is about matching power supply with demand. People say the wind doesn't always blow, the sun doesn't always shine. Well, can you make it reliable? Well, we did a study a few years ago looking at California and using California demand for 2006 and 5, and that's the black line in each of these plots. And these are two particular days. And then taking that demand and see if we can match it with existing geothermal, existing hydro, but just increasing wind and solar. So the light blue on these graphs are wind, and that's using wind data given several locations in California. The yellow is solar, PV. The orange is concentrated solar power. And the blue is hydroelectric, which is used to fill in the gaps. And you can see, and then the red is geothermal on the bottom. You can see on these two particular days, we can match the power demand, the black line exactly. The gray above the black line is spinning reserves of natural gas, which was never used on these 2 days. In fact, we found that the natural gas was never needed except for 0.2% of the hours over 2 years. So we can match it every hour of every day with just wind, water, solar technologies. And this was without even doing things like demand response management, oversizing the grid with renewables to make it easier to match demand, and then using the excess electricity for producing hydrogen, or using very much concentrated solar power with storage. So anyway, we think it's more of an optimization problem to match the power demand. And then finally, I just want to show what's the timeline for the transition. If we look from 2010 to 2050, well, if we don't do anything, we go from 2.4 terawatts of US power demand in 2010 to 3.1 terawatts. That's the top line, which is the business as usual line. If we convert everything to electricity plus electrolytic hydrogen, then we get about, we go down to the second line, which is the reduction of power demand by 1 terawatt in the US just due to the efficiency of electricity. Then we can reduce it another 0.2 terawatts, or probably even more, just with end-use energy efficiency improvements to get to the 100% line, and all the rest of that would be wind, water, solar produced. And we expect that by 2020, if we can get all new energy to be clean, so all new cars, electric cars, all new electricity, wind, water, solar electricity, and then replace existing infrastructure as it retires with clean energy, and then to have aggressive policy measures. By 2030, we would have replaced 80% of the infrastructure to 80 to 85%. By 2050, 100%. And we would have eliminated all these problems. So the overall summary is here, if we convert everything to wind, water, solar, and electricity, hydrogen in the US, we'd reduce power demand by over 37%. Actually, yeah, it's close to that. Eliminate 63,000 US air pollution deaths, and $730 billion in global climate costs, create 5 million 40-year construction jobs, 2.4 million 40-year operation jobs, cost 3.9 million fossil fuel and nuclear jobs, save about $4,400 per year per person in direct energy costs just by looking at the price differential if we go business as usual versus wind, water, solar, looking at the trends. And another $3,100 per year per person in health and climate costs, 2050. We'd require only 0.44% of the US land area for footprint and 1.7% for spacing. There are several methods of addressing the variability of wind, water, solar technologies. We didn't find material limits, but recycling may be needed for some components. The barriers are primarily upfront cost because it's very capital intensive. Transmission needs which are not a technical or economic barrier, but more a social political barrier. But then lobbying and politics is the main barrier. And just finally, if you want more information, there are a couple of websites here that have all the papers associated with these plans. And you might be interested in the Solutions Project, which is a group that's dedicated to taking these science-based plans and trying to implement them at the state and country and world levels, and trying to involve businesses and business and culture, and along with the science and technology. So anyway, thank you very much, and I'm happy to take any questions you have. Thanks.
So we have time for a few questions. Please raise your hand, wait for the microphone, and stand up when you get the microphone.
I remember reading this in Scientific American a few years ago, and the comments were pretty brutal for that article, criticizing it for not taking into account the sunk costs of the pipes in the ground for the traditional oil infrastructure. I wondered what your response was to that.
The sunk cost of, well, there is a sunk infrastructure, but so we're going to be replacing, when we have new energy demand, we'd be replacing with wind, water, solar. When existing plants retire, then we'd be replacing, instead of building a new coal plant, we're going to build a solar farm or something. So we're relying on natural retirements as well as some forced retirements, so coal plants are coming out of the ground. But those sunk costs are pretty trivial compared to the health and climate costs that those plants are causing. So I would, yeah, but there's going to be natural retirements. I mean, just to put it in perspective, if we did this worldwide, we'd have to spend $100 trillion in capital costs to replace everything. But the fossil fuel industry spends, I think the number was $6 to $7 trillion a year. So it would basically pay for the system in, you can count the years, it's in 15 years or so.
Right now, we don't use a lot of hydrogen, but we do use some. And we have excess electricity at certain hours of the day in certain areas. Why isn't that, the electrolysis with that electricity, the primary source of hydrogen?
Exactly. Well, that's part of this plan. We would, instead of curtailing, because right now when we have too much wind or too much solar in the U.S., a lot of times it's wasted. It's not used. But in Denmark, they use extra wind for district heating, so they use it to heat the cities. And another plan is to use it to produce hydrogen by electrolysis, so you can then store it, or some other storage, or you can use it for pumped hydro. Actually, like a third of all the hydroelectric power in California is pumped hydro. So you can actually just pump it up to a higher reservoir when you have extra electricity. So there's no reason at all that you can't do it. It just hasn't been done a lot. And that's, as part of this plan, that would be one of the goals, would not be to curtail any wind or solar.
I was wondering if you can talk about how much energy storage is needed. From one of your slides about demand response, it sounded like you were saying that it could be managed in real time. But in addition to generation being random or at different cycles, the energy usage is also in different cycles as well. I was wondering how that all comes together.
Well, certainly the more storage we have, the better. The study that I showed you indicated that, if push came to shove, we could get away with not a whole lot of it, but the more we have, the better. Now, in these plans, hydroelectric is a form of storage already, and concentrated solar power with storage is a form of storage that we accounted for. And so those are two forms of storage, but there are additional forms of storage. It could be like in hydrogen, it could be in batteries, or it could be in flywheels. It could be in soil, like there's a town in Canada that heats the soil in the summer and then uses that heat in the winter to power 90% of their heating. So the more the better, but our study and another study show that you can do like 98 to 99% of the grid reliably without a whole lot of storage except for hydro and concentrated solar power.
Okay.
I have a question back here. I was interested in this question for the last 6 or 7 years and looked at the problem of energy density with regard to mostly flying airplanes and the issue with regard to liquid fuels versus hydrogen. I looked at algae as being 100 times better producer of hydrocarbon-like fuels, diesel, but also other fuels through syngas. And it looked like algae would work provided you did it offshore and didn't use land and used wastewater instead of water and fertilizer. I don't know if you're familiar with the project. It was funded at $10 million by NASA for 3 years. And we saw that algae would really replace a big chunk of our liquid fuels. But with regard to flying airplanes with your system, is it hydrogen-based? Is that your plan?
Well, the cryogenic hydrogen, which would be, so you'd need aircraft that have larger volume, because hydrogen is not very dense, so you need more volume, but it's less massive. So there have been studies in the US and in Europe showing that the total drag on the aircraft would be about the same. The Russians built a cryogenic hydrogen aircraft in the 1980s, but it wasn't economic at the time, and the space shuttle ran on cryogenic hydrogen. So it's technically feasible. All the aircraft companies have looked into it. Right now they just have a status quo, so they don't want to change anything. But there's no technical reason it can't be changed. In terms of algae, we're looking at air pollution and climate, and when you burn the products of algae, you're just burning a fuel that you have combustion products that contain black carbon, carbon monoxide, hydrocarbons, including NOx and other things. So you still have a similar amount of pollution. Photosynthesis is only 1% efficient. So you can take, even though, I mean, you can't really skimp on the land. You're either going to spread it out over lots of land, or you'll build these towers, which will be really inefficient in terms of photosynthesis. So as a result, you need it takes about 30 times more land, 30 to 80 times more land. The energy you get from the biofuel is 30 to 80 times less than that of putting solar photovoltaics on the same land. Because the photovoltaics you can get, they have efficiencies in the order of 25%, or 22% at the most. But photosynthesis is much less.
Yeah, the photosynthesis can be up to 5 or even 7%, and the system we designed doesn't use any land, 0 land. It's all offshore.
Okay, well, I'm interested to look at it, but it has the problem of combustion. It's still the main problem.
Sorry. Go ahead.
I'm just wondering if you could talk a little bit about solar thermal energy and whether or not you think that's a good idea to invest in.
Well, there are different types of solar thermal, like the concentrated solar power is a form of solar thermal, or are you talking about the rooftop?
Having steam generation from solar thermal and running generators from that.
Well, so concentrated solar power is where you focus light onto mirrors, onto a central tower receiver to heat a fluid such as a molten nitrate salt. And then you can store that molten nitrate salt overnight and then use it to run it next to water to evaporate the water to generate steam for a steam turbine. And that's great. So it's a little more costly right now, but because you have the storage associated with it, then it makes it extremely valuable. You can really produce any profile you want of electricity production. So it's definitely worth using. So that's why we try to put it as many places as possible. But you need direct solar radiation. You can't use diffuse radiation too much.
Well, thank you so much for coming. I had a couple of questions. You talked about the area of like wind turbines and things, but what about the material that's needed to actually make these and manufacture them? So manufacturing plants, the cost is, or you talked about the cost, but more of like the energy required to make these. And then also you talked about how wind turbines off the coast can reduce winds from hurricanes, but how can that be negatively seen as well? So we might be changing the climate when we put these wind turbines up. Have you seen research done, or do you have knowledge of how it might actually be reflected in a negative way or in a different type of climate structure?
Yeah, well, let me answer the first question. The energy embodied in producing a wind turbine is about 3 to 6 months of running the turbine. So the turbine lifetime is about 30 years. And so for the first 3 to 6 months, you're basically generating the electricity you need to produce which might have been from fossil fuels. So it's about 98% carbon free if you use today's energy infrastructure. But eventually, if we have 100% renewable energy, then it would be 100% carbon free. In terms of metals, like you need steel and cement, but you also need some rare earth elements. But we looked at the rare earth, like neodymium. There's about 7 times more neodymium available in resources than you need to provide all the wind turbines you need to power the world. In terms of the wind turbine impacts, we did 2 studies, one looking at covering the entire world with wind turbines, covering all land with wind turbines, then putting 4 million wind turbines, which would be enough to power 50% of the world. And in the 4 million case, which is the practical case, there's virtually no large-scale impact. You got local impacts downwind. You reduce wind speeds locally. But if you cover the US or the world, what you find is actually they cool the climate. In fact, wind turbines will cool the climate. They warm the land locally, right downwind of the turbines, because they reduce evaporation. And evaporation is a cooling process, so if you have less evaporation, you warm the land. But because you have less water in the air, you get less condensation in the air, and condensation is a warming process, so if you have less condensation, you cool the air. So those 2 things offset each other in terms of temperature, but because you now have less water vapor in the air, which is a greenhouse gas, you cause less global warming. It's the most abundant natural greenhouse gas. So we found that there's a net cooling of climate due to putting all these wind turbines up. But at the numbers we're talking about, 4 million wind turbines for half the world's energy, it's really a trivial impact on the water budget overall. You'll get local impacts, reducing wind speeds, maybe changing precipitation locally, but you're not going to have large-scale climate impacts from those turbines.
Hi, that was a great talk. I was just wondering if the plans looked into distribution logistics, so distributing places that have high solar energy and high wind speeds to areas that need the energy to use.
Well, so the transmission system, that's kind of where one of the barriers is, not so much technical or economic. You would, well, in the US, you have a lot of wind in the Great Plains, for example. You also have a lot of wind offshore the East Coast. But every state has some wind, except in the South, it's not that great, but there are still places in the South. So you would, and the same thing with solar, you have a lot of solar in the Southwest. Well, every state has some amount of solar. But in particular for wind, you might need long distance transmission. So there's just going to be a balance. Take, for example, the East Coast. Is it less expensive to build offshore wind, which you have very little transmission of, and it's right next to where people live, or have wind that's 2 cents a kilowatt hour in the Great Plains and then build transmission to the East Coast? I mean, that's the question that arises. I mean, there's already a transmission grid across the whole US. The question, you'll probably need to enhance it. And that's more of a zoning issue. A lot of people just don't want to add transmission. And so it's not a technical or economic issue, but it is a political issue. And that's one of the possible barriers to doing this on a large scale.
So please join me in thanking Dr. Mark Jacobson for an excellent presentation. Thank you very much.